I wanted to thank organizers for giving me an opportunity to present some of the work. And so this talk is going to be about volume of random geodesic complements. And this is joint work with Yannick Rivka, Didac Martin-Trinad, and Franco Vargas-Balada. So this is it. And then at the setup, we're going to consider like a closed hyperbolic surfaces X. So this is just like a surface with some negatively curvature. It's uniformly -1. And it's complete, it's important, it's a complete surface. And then on that, you can consider loops. So like in the picture, you see like one loop, that's like a closed curve. And whenever you're like in this negatively curved setting, every loop can be tightened either like a geodesic or it just collapses on top of it. So what you want to consider is geodesic loop. So you take whatever loop you have and you tighten it down so that it becomes geodesic, which means it's locally length minimized in this setup. And then we have this more topological condition that means it's primitive in filling. So a loop on a surface is primitive if it's not the power of some other element. So if you think about fundamental group, gamma is primitive, gamma is not like alpha to the k, where alpha is some other element and k is some integer, not necessarily positive. And then filling, it just means that if you look at this picture, right, you get something that's rather complicated. So this meaning that rather complicated means that like the loop kind of goes everywhere in the surface. So if I start to like cut along the red curve gamma, I get like this, and then I get like a bunch of boundary components which are like this thing. And all these components that you're left with, you want them to be disks, or if your surface admits boundary requests, you also allow like disks with one puncture. So that's so to say anyway. So this is what primitive filling geodesics are. So we want the curve that it's geodesic. So for example, it's a minimum position, and if it's not a power of something else, and then we want all the complementary regions to be disks. So if you have an object like this, then when you look at the projective tangent bundle of your surface, or even the unit tangent bundle for that, what that matter. So you take all vectors tangent to the surface at a length normal one, that's a unit tangent bundle. And then to get the projective, you identify like the going forward and going backward direction. So if you take this three-dimensional gadget, and then you drill out a copy of this loop from this gadget, and you want to drill it out in a particular way. So because we're looking at the projective unit tangent bundle, there's a preferred lift of the curve, which is called the canonical lift. And essentially, in the projective bundle, you just lift with respect to the tangent line field. So that gives you like a well-defined point in PTX, corresponding to like a point on the red loop. And for the unit tangent bundle, you essentially choose an orientation, and then you drill out the forward orbit or the backward orbit. You just take the tangent lift essentially. So if you do this, you obtain now like a three-dimensional manifold in which you drilled out a loop. And there's a theorem that, more an observation that was first done by Fuller and Nassib back in 2013, that this is a finite volume of a free manifold. But also there is a really nice blog post by Danny Caligari about that gives like a proof of the statement. However, they use a lot of geometric properties of the geodesic flow. And me with another corroborator in 2020 realized like the proof in which we relax a lot of the hypotheses and we don't use, for example, these techniques coming from geodesic flow, but really hands-on three-dimensional topology arguments to show that if you take a Sapir-Fiber free manifold with some kind of reasonable loop inside, then it's hyperbolic if not if the loop is primitive and filling. And so then once you get this hyperbolic manifold, you want to figure out what the volumes are. That's kind of like a first invariant, because by master rigidity, the volume is a topological invariant if these things are not just like a geometric invariant. And so there's this upper bound by Bergeron, Pinsky, and Silberman, which to some extent it's kind of generic, but also like not very good for more deeper reason that we don't have talked to this podcast about. But you take the modular surface, which is a quotient of H2 by PSLTZ, which is kind of like looks like this, where this is a CON2 point and this is like a CON3 point, and this is like a cone cusp, and then you draw like some geodesic, and then the same setting on before, you get the complement of the unit tangent bundle of this thing. It's a hyperbolic, and the unit tangent bundle of this thing is just the complement in the free sphere of this green knot, which is the traffic knot. So, this way they're like essentially studying knots in the traffic complement in the free sphere. And for this, there is this amazing fact is that any such filling geodesic here, you can encode quite nicely for this template. So you go X around once here, and then you could do like many times X, and then you're like here, and then you have to go to Y, and you do like sometimes just around Y, and then you keep going. So this, after autotapping, is all possible tangent planes to fill in geodesics on the modular surface. And then by doing some estimates with the triangulation, they show that essentially this is they get like a linear upper bound in the terms of the switches in this template. So if you have X, Y, X, that's like two switches and so forth. And then they relate this. There's a quite easy way to relate this to the hyperbolic length in a linear way. And then, so they get like an upper bound that's linear for the modular surface. And then using like branch covers and some other like general results, they bootstrap this to get like a linear bound for the manifolds that we were looking at in the previous slide. The issue is that this constant, which also depends on the hyperbolic structure that you choose, it's very hard to find. And this is not surprising because this manifold here, and so like this quantity here, does not depend on the mapping class group action, while this right-hand side changes. So like you could try to minimize this, so you can enjoy like a hard problem. And then there's this combinatorial lower bound by me, Rodriguez, my collaborator, Rodriguez. It's very nice. So you take a surface, and then you decompose it into, let's say, pair of fans. And then you just count like you intersect your loop gamma to this pair of fans in a minimal position. Then you count how many arcs you have. So this is kind of like an example where this is one arc, these are two different arcs, these are three different arcs, two again, 3 and 1. These are all possible simple arcs that you can have in a pair of fans that are like homotopically distinct, because you're allowed to do homotopy like of the boundary as well. But then the way that you make this fingers is by taking like non-simple things. So you take an arc that it comes in, then it twists a bunch, and then it cuts itself, and then it twists a bunch, and then it cuts itself again, and so forth. So these will be like the real thing that contribute to this left-hand side. And this is the proof. So it's kind of simple, and it follows some classical things to Eggleston, Thurston theorems, and cross-cutting argument. So what we wanted to do was like, can we get like a lower bound notion for the volume? And ideally, we wanted like something that depended on length, just because with this like nice length lower bound. And the answer to this question is quite simply no, because if you take like an epsilon nozzle map, which is like a very mixing map, then the length of that curve will blow up to infinity. But all of the manifolds that you have are like in the same homomorphic classes, so their volume stays constant. However, you can make a little bit more interesting examples, which we call like twist families. And they were like originally discovered by Andras. But I don't really want to have time to talk about those. I'll just show them in a picture. So, and what we did using since there's no deterministic solution, then we want to think about like a generic geodesic. So like you pick one of this filling primitive loops at random, then can you say something about the volume of that? That's kind of like a standard thing when deterministically you don't have to do much. And so like in particular, you would want for kind of meta reasons that a sequence of random geodesic has to converge to like the Liouville measure, which is this very nice measure on the unit tangent bond. As far as data goes, Brands, Sapitsky, and Silverman, they computed the volumes for like a very specific family coming from some number of phonetic constructions. And so you can see they get some pretty linear behavior, okay? But this is how long is the loop on the modular surface, and this is what the corresponding volume. All of the segmental data that you can do has to be done with respect to the modular surface, because that's what we can use our technology tools like Snappy, which is very good at computing volumes in not link complements. And so, okay, so this is kind of just like linear behavior for the whole thing, but that's maybe not the case, because again, you're only checking like, finitely many terms. And so your modeling trader, other collaborators, they computed a different set of things. So what they did is they looked at all geodesic of length at minus 16. So it's a much smaller scale than the previous picture. And then they computed the length. And first of all, there are like a couple of differences from this graph and the previous graphs. The previous graph was, let's say, like kind of linear. And this one, it's very obviously not, right? I mean, this kind of stuff. And moreover, you have like these sequences like this, or even like this, even if it's a slower one, that are kind of like flattening out as it grows. And these are exactly examples of what I was referring to as Swiss families, which are loops that are never homotonic to each other, like not even the same mapping class, but for which like the volume is uniformly bounded. So again, like if you want to find a lower bound that depends on length, you're never going to be able to find it, because the length of the sequence, right, which is going to keep going on forever, is going to stay like bounded, but the volume is also, sorry, the length of the sequence is going to blow up, but the volume is bounded. So that's why you want to do like something random. So what is a random model? So you take a surface with some hyperbolic structures, and you sample a unit tangent vector at random. This is using the Livio measure that I was talking about before. And you might have to throw away like countably many directions. So like it's a measure 0 set, which doesn't matter. So now that you have this vector, then you just flow for a long time. So you go around the surface like this, so that at some point, which is what we're calling this TOV, you come back that are very close to each other, right? So this vector, it's very close to this vector in the sense that like close to the surface, and their direction is also close. And then you shortcut. So you draw like a little geodesic arc that connects them. So this now gives you a loop, which you then pull tight to obtain a fill-in geodesic. The fill-in comes from mixing and ergodicity properties of the geodesic flow, and the fact that you went for like a long time enough, that was the TOV. And then the primitive, it's not necessarily, so like if you just pull tight, you're not going to get something primitive in general, but you can consider its primitive subgroup. So like the thing that loop it's a power of, that's what we call, that's going to be our end gadget. And if gamma was primitive and it's a power, then the thing that it's a power of is also primitive. That's like a standard fact. So this is a way of generating, what I just given you is kind of like a funky way of generating like random filling primitive curves on the surface. Okay, then we check some properties of the model. This is a sanity check. That the model converges to the Livio measures. So this also guarantees that it's filling. For almost every mu, then the volume of this corresponding thing blows up. So for almost every vector you pick, the volume goes to infinity as the length goes to infinity of the loop. And this like in general is not going to be primitive. So the result that my result that we have is a can be finite density setup. So if you take like a surface of genus G with some hyperbolic structures, you can look at all geodesics of length R. That's a finite number. That's what the G of R is. It's finite because of hyperbolicity. And then you say, our set, in which they said that we care about, so the things that we construct with that process, we call that AOR. So elements came out of that process that length at most are in AR. And then this is used as density 1 if as R goes to infinity, the limit is 1. So that just means that you might not see every geodesic that you have, but you will see like a full measure proportion of the geodesic. And then our main result is you take hyperbolic structure X, and we wanna to make this number a little bit nicer, but it works for general structures. We want to pick a specific one. By a specific one, I mean take a bunch of isometric pair of pens, and then we just glue them together without twist to the orthogonal surfaces. That's the unique requirement. And so if delta is the dimension of the limit set, which is in some sense a measure of how big the pens is, and then we get the following result that for every eta, that's just like an auxiliary parameter, you have a sublinear class of functions, for any sublinear class of functions of that type, then the collection of primitive filling geodesic, so this is the AR before, that satisfies the correct band inequality is 1. So this is kind of a mouthful, but asymptotically, what that means is that so eta can be taken arbitrarily close to 1, and theta can also be taken arbitrarily close to 1. So this whole exponent here, it's really kind of like 1/2. Like you can think of it to be kind of 1/2. So, and this is just this is just like to get a fancy result maybe, but morally you're saying that things are going like the square root, because this is like of the line. So you have generically you have growth rate for the volumes in terms of length that it's comparable to the square root function. So the volume is, let's say, at least some constant that's maybe very, very complicated, and it depends on the metric, times the square root of the length of your geodesic. So this leaves quite a gap with the data that we had, with some of the data that we had before, like the one that was computed by Bergeron, Pisky, and Silverman, because that was very linear to some extent, but that was also a very specific class of geodesic that enjoyed all sorts of number theoretic properties. And for example, you couldn't really see the Swiss families that I said a few words before. Well, this is kind of it's a more robust result in the sense that this is for like almost all geodesics in the sense of asymptotic density. And the quick idea of how you prove this thing is you chop up the unit tension bundle into various chunks, and the chunks are the set of geodesics. So are like each chunk lives in a pair of pens, and so these are like the set of geodesics that are homotopic to a fixed orthogeodesic. So that's what they're corresponding to, and the idea is because we want to use that combinatorial lower bound in the end. And the nice fact is that you can compute quite easily on the nose what the volume of this OI is, which is something that we need. So again, to repeat, OI is just a set of geodesic arcs in a pair of pens that are homotopic to a given orthogeodesic. So this is some three-dimensional slice. Then you want to use the combinatorial lower bound, but like I said before, to get the volume estimate by counting how many of your gamma arcs as t gets large fall into one of these OI. And so the hard part here is just how to relate this like counting problem to our geodesic model. So the main point is that we need to understand for a generic vector how many distinct regions OE we visit by flowing for like a long time. And specifically, you want to check this not even for like the closed loop, but just for the geodesic ray. And so the counting problem at the end is, okay, so you need to actually refine a little bit the partition that I mentioned before. So the BIs are not exactly the OI because we need to use smooth term functions. But then you get that the volume is at least this like CTB kind of number, where CTB is the integer times. So CTB is counting time you do one step of the geodesic flow, 2 steps of the geodesic flow, 3 steps of the geodesic flow, and you see you're like in some set BI. So if for the first 15,000 years of the geodesic flow, you're always in the same B1, then CT of V is like 1. So this is exactly the number of partition sets that you visit by flowing from time V from vector V. It's going to define. And the way we do this, it's by using a lot of really like precise analysis, and that's why we needed like to use smooth functions here and not just characteristic functions. And essentially comes down to proving a multiple Ke mixing result for the geodesic plot that I don't really want to describe in detail, but I'm going to give you the formula. So this is kind of one of the big chunks of the proof. So you need to, we know that the geodesic flow is mixed, but and we also kind of know what the rate is, but we want to know to make our compilation free speed, how it mixes like, arbitrarily many functions. So and we need to get like really good controls. So we kind of know what these constants are, but mostly what we want to know is like the growth rate in n, and like how many, because of how many things we mix. And there's this exponential term, so it's also kind of explicit with alpha, and this is about the sub-Euler free norms of the functions that you consider. And so what we will do is we will have like some nice smooth bump functions on the OI sets. That's what the PI thing will be. And then we need to build this thing so that we can control like very nicely the like sub-Euler norm, so that this kind of big expression, it essentially balances out as n goes to infinity. Okay, so this is kind of like the idea of what we prove, and this is kind of where like the horrible estimate comes into. And that's all. Thank you.